Okay. See
So,
only few students. However, we cannot wait. I will start directly because this lecture, I think, will take uh, the full time, and also it's subject from the exam, so we have to finish this subject because it's in the exam, this subject. Okay, so subjects for the exam, everything until what we will take here, until the end of this lecture note, all in the exam. So lecture note 1 until 6, 1, 2, 3, 4, 5, and 6 also in the midterm exam. As I told you, the midterm exam will be in OIS system. Um, Any question? How will be the exam? We did not decide yet, actually. Uh, but we have two choices. One choice is to give you the file of the exam at OIS system, then you use your handwriting, answer the questions, scan the questions, then send the file using OIS system. This like any assignment. This first choice. The other choice is to answer the exam directly at OIS system. I will tell you which one we will choose during this 2 days. Anyway, you need to study all the lectures note. Okay, so today we have a new subject which is recurrence relation. What's the meaning of recurrence? Actually, recurrence means something repeat itself, like recursive function. I think you take in the programming recursive function. So uh, recurrence means something repeat itself. Let me just sure that we start the record. Okay. Okay, so our subject in this lecture, recurrence relations and solving one type of this recurrence relation, which is solving linear recurrence relations. Okay, first of all, maybe in the school you saw some series like this, okay, or sequence like this, give you some sequence like 3, 6, 12. So ask you what's the next uh, term or next item will be. Here another series, it's a start from or another sequence, 1, 1, then 2, then 3, then 5, then what is the next term? Okay, for the first one, it's easy to know that each term it's um, double or previous term multiplied by 2, double of the previous term. So 6 actually it's come from 3 multiplied by 2, 12 it's come from 6 multiplied by 2, then next one will be 24. It's easy one. Okay, this one, if you look to the second one, it's more difficult, little bit, but if you look here, you will see that each element actually is the summation of the previous two elements. So 2, it's come from 1 plus 1. 3, it's come from 2 plus 1. 5, it's come from 3 plus 2. Then next term, it's 5 plus 3, the summation of the previous two terms. So it's 8. Okay, next term here for this one. Okay, it's easy. 48. Next one here, 8 plus 5, it's 13. What's the question? What's the value of term 100, for example? Okay, this term 0, term 1, 2, 3, 4. What's the value of term 100? To know it, you need to know term 99 and term 98 and so on. Yes? Of course, no. This series, we can write it as a recurrence relation like this. Here, we said that each term, for example, term n plus 1, it's equal to multiply by previous term, which is an. So term a means the term, okay, n plus 1, so means the index of it, n plus 1. So for this series, it's actually 2 multiplied by the term n. That's the previous term n, previous term n minus 1, and so on. But still we have same problem, how to get term 100. To get term 100, for example, after we find this recurrence relation, we have to find the general term or solution for this recurrence relation. If we could find the general term or the solution for this recurrence relation, then it's easy to get any term. So, our job in this lecture, if we have a sequence or relation like this, we need to get the recurrence relation, means like the recursive function for it. What's the repeated way? What's the relation between terms? Okay, this is the meaning of the recurrence relation. After we get recurrence relation, we need to find the general term for this recurrence relation. This general term could be any term, yes, then it's easy to calculate any term for this recurrence relation. This is the issue here. So this one, it's the recurrence relation for first one. What's the recurrence relation for second one, for this one? Okay, first of all, this one is the recurrence relation for first one. But this is not enough. Why not enough? Imagine that I start from 2. Then next term will be, depending on this one, will be 4. Next one will be 8. Then look, this sequence, it's different than this sequence. Why? Because we have different starting. So it's not enough for the recurrence relation to describe or identify the sequence alone. We must mention something called the initial value or the initial term. Here, we called it term 0 or first term, term 0. So A means term, A naught or A0. In the mathematics, we called it naught instead of 0. But you can call it A0 or A naught, it's up to you. So A naught means first element in this series is 3. Now we know first element and we know the recurrence relation. Its full description for, or full correct description for this series. I know that I must start from 3, then apply this one. Each element, it's 2 multiply of previous element. So this one, 2 multiply 3, it's 6. The next one, 6 multiplied by 2, it's 12, and so on. Okay, so for describing the sequence, we need the recurrence relation plus the initial terms or initial value. Could be one term, could be two terms, could be three terms, the initial terms. Okay, let's look to the second one. Second one, or this one, it's called Fibonacci sequence. I think you know it from the programming. Okay, in this sequence, we have each term, it's calculated from the summation of previous two terms. So if we write the general form for it, third term, or term n plus 2, it's equal term n plus 1, term or n plus 2, it's equal a n plus 1 means the previous one, plus an means the previous of the previous term, means the previous two terms. But to complete it, first two term in the sequence, it's constant or known, must be 1, 1 first two terms. So we have two initial terms, which is a naught equal 1, a1 equal 1. So this is a full description for the Fibonacci sequence. Okay, so what is the sequence? Sequence is a function of set of integer. It's come as a relation between the terms. So the sequence of the term. So each term could have a relation with other terms to become a sequence. Okay. A recurrence relation for sequence, when we write it like this means a sequence an. What's the meaning of recurrence relation? Recurrence relation, actually, it's an equation that expresses an in terms of one or more previous terms. So, term an, we describe it using one or more of the previous terms. So, the relation of a specific term an with previous one or two terms. This is the recurrence relation. Okay, what's the relation between the sequence and recurrence relation? Sequence is called a solution for the recurrence relation if its term satisfies the recurrence relation. So, if each term in the sequence, if you use the recurrence relation with each term of the sequence and you get the correct value, then we name this sequence as a solution for the recurrence relation. Or the opposite side, the recurrence relation, it's the recursive definition of the sequence that could help you to get any term of that sequence. So first of all, let's take some examples for the recurrence relations. Okay, here we have sequence an, and this sequence satisfy a recurrence relation. So this sequence an means it's a solution, satisfy means it's a solution for this recurrence relation. So which recurrence relation? This recurrence relation. The recurrence relation said an equal an minus 1 plus 3. This means each term is the previous term plus 3 for all integer n from 1 to blah blah from the so 1, 2, 3 and so on. Okay, and suppose that a naught equal to. So first term in the relation is 2. Yes, because a naught means first initial value, it's 2. Okay, now get a1, a2, a3 means second term or term a1, term a2, term a3. It's easy. Term a1 means this recurrence relation. Instead of n, we will use 1. So an means a1, terms a1 equal a 1 minus 1, yes, because n it's equal 1. So it's term 0 plus 3. So a1 equal a0, which is, or a naught, which is 2. It's given to you here. So this equal 2 plus 3, which is equal 5. So we get term a1. Same way you can get term a2. Okay, we understand that each term it's the previous term plus 3. So a2 it's a1 plus 3, which is equal. A1 we already calculate it here, which is equal 5. Then plus 3, which is equal 8. And so on. A3, same idea. It's a previous one, which is 8 plus 3. So it's equal 11. Okay. But we still have the same problem, which is A100. How much? Cannot know it simply from the description of the recurrence relation. From this description, you cannot get A100, for example, or A50 or A150 means term 100 easily. You cannot get it. You can get it if you get the general term of this recurrence relation or the solution for this recurrence relation. We will take it later, next. Okay. Another example here, we have the sequence an and uh, its recurrence relation is this one. This is the recurrence relation. An equal an minus 1 minus an minus 2. What's this mean? This means each element, it's the previous element minus the previous of the previous elements, the difference between the previous two elements. This the mean of this sequence, okay. And we start from a naught equal 3, a1 equal 5. So first two elements in the sequence, 3 and 5. What's the next element? It's easy to get next element. We said that each element, it's different or minus of the previous two elements. So if we said we need A2, here we need to get A2, A3, because we already have A naught, A1. So A2, it's equal A1, because 2 minus 1 here, AN means A2, equal n here is 2, yes? So it's equal 2 minus 1 means A1 minus 2 minus 2, which is 0, so this A naught, so minus A naught, which means 5 because A1 is 5 minus 3 naught is 3, which is equal to, okay, A3, it's A2 minus A1. A2, it's 2 minus A1, we get it from here, which is 5. So the result is minus 3. So term A3 is minus 3, and so on. Uh, Also, same way, we can find A4, A5, A6, A7, and so on. Okay, so solution of a recurrence relation. How to get a solution, or what is the solution, and how to get a solution for a recurrence relation. So we can use this solution to get any term easily, because as you can see from the recurrence relation itself, okay, we can get the terms but in sequence. But if we would like to get the term 200, the term 150, or so on, we cannot calculate only one term separately from the other term or the previous terms. So to do this, we need to find solution of the recurrence relation. The solution is uh, could be more than one solution for the recurrence relation. Any sequence, any sequence whose terms except the initial term satisfies the recurrence relation. Why except the initial term? Because the initial term have a specific value, constant value. It's not related to the recurrence relation, but it's the starting point for the recurrence relation. Okay, so any sequence whose terms satisfy a recurrence relation is called a particular solution. We could have more than one solution. So to solve a recurrence relation means to find explicit means a clear expression for the general term. What's the meaning for the general term? Means term n. If you could find explicit expression for general term n, then you can say instead of n, you can say 100, term 200, and so on. Okay, so uh, this solve or explicit expression whose terms except the initial one satisfies the recurrence. Let's take examples. Okay, we need to find solution for this recurrence relation. You know it. Yes, this first recurrence relation. First example, first recurrence relation. How to solve this recurrence relation. To solve this recurrence relation, actually, we have many ways. Let's take the simplest way. The simplest way is to find solution for the few first terms. For example, we find term 1, term A1, term A2, term A3, and so on. First few terms of this relation. And then we try to find pattern. Okay, pattern from this relation means something that repeated in this sequence terms. Then this pattern, if we can make it general, then we can find a general formula or general solution, general term for this recurrence relation. Let's take this one. So from this one, we want to take first a few terms. Okay, we already have term A naught. We will take term A1. Okay, term A1 means N0 because 0 plus 1 means 1. So it's equal to A0. Why term A1 here means N0? Because each term it's N plus 1. So term A1 means N, it's equal 0. So if N equals 0, we have term A1 because we already have term A0. It's equal to A0 because we said each term it's 2 multiply of the previous term. Okay, which is equal to multiplied by 3. What's the 3? Term A0. We said term A0, it's a 3. Okay. Next one, term A2. It's 2 multiplied by term A1. Okay, so it's 2 multiplied by term A1. Term A1 here, we already calculated it. So it's 2 multiplied by the value from A1, which is 2 multiplied by 3. Okay, term A3, it's 2 multiplied by A2. 2 multiplied by the values that come from A2. Okay, let's write it. So this one, 2 multiplied by 3. This one, we have 2 multiplied by 2, means 2 to power 2. This one, 2 multiplied by 2 multiplied by 2 means 2 to power 3. Okay, and this one, 2. 2 means what? 2 to power 1, because anything power 1, it's same. So if you look here to each term, okay, here you have 3 multiplied by 2 to power something, to power 1 here when we have A1, power 2 when we have A2, power 3 when we have A3. So AN actually is a general term of A, which is AN. Actually, it's equal to power N multiplied by 3. So this is a general term. From where I get it? From the relation here between the terms. We find the value of the first term, the value of the second term, the value of the third term, and from these values, we find that there is like a sequence here or something repeating. Okay, 3, 3, 3, it's constant, 3, multiplied by 2 to power a number. So multiply by 2 power which number? This number, it's same like the term number. So if we need term an, it's actually equal to power n multiplied by 3. This general term, now after find this general term, so first step is to find first few terms. Second step, it's to find pattern in this. Pattern means something that repeated in each. And from it, we can find formula. Formula or means the general term or general description. Third step, we need to confirm that the general term or description that we reach is a solution. What we said here, a sequence or the general term, it's a solution if it satisfies the recurrence relation. So a sequence is a solution if it satisfies the recurrence relation. What meaning? mean we will apply this term, general term, for the recurrence relation to see if it satisfies it or not. If it satisfies it, then it's correct, but this is not enough because it have to satisfy it and satisfy the recurrence relation and satisfy also the initial term. So you can set this 3.1, it's to check if it satisfies the recurrence relation. 3.2, step 3.2, it's to satisfy the initial terms. You can first satisfy initial term, then the recurrence relation, or recurrence relation first, then initial term. It's up to you. How to find if it satisfy it or not? It's easy. It's like this. We have the solution. We will apply this solution for this recurrence relation. So if this general term, it's satisfy, means give us the recurrence relation, then it's a true solution for it. So we will start from this recurrence relation. So recurrence relation said like this, we have an plus 1 equal to an. Now get this an from the general term here. So what this mean? This mean we will apply this solution for the recurrence relation. So let me just, this is a recurrence relation. Okay, we will start from it and we will apply the general term or the solution for the recurrence relation. So we will take this one here. So an plus 1, it's equal to, okay, 2 multiply by what? 2 multiply by, instead of an, now write it, it's 2n multiply by 3, yes? This one, n power 2 multiply by 3, it's the an. We put it here. Okay, multiply it, so an plus 1, it's equal, 2 multiplied by 2, it's 2n plus 1. When you multiply same number, you make summation for the power, yes? So this 2 power 1 multiplied by 2 power n, it's 2 power n plus 1 multiplied by 3. Okay. And this one give us what? Same idea. You can start from an, you can start from this one to reach this one, you can start from this one to reach the other one. Okay, so now let's continue. This give us 2 multiplied by 2 power n multiplied by 3. This one actually, it's an from here. So it's 2 multiplied by an. So again, it's me repeated again now because here a lot of lines. So we will start from an plus 1. It's equal to n plus 1. Sorry, I I mix the solution. It's the opposite. Sometimes we can start from here, sometimes from here. I started in this solution from here, actually. So if we said this is a general term for an, I need an plus 1. So an plus 1, it's equal to power n plus 1 multiplied by 3. From where I get, instead of n, we put n plus 1. Instead of n, in the solution, we put n plus 1. So we will start from the solution and get the recurrence relation. If from this solution we get the recurrence relation, then the solution is correct and satisfies the recurrence relation. So this equal to power 1 multiplied by 2 power n multiplied by 3. Okay, so this means 2 multiplied by 2 power n multiplied by 3, it's an. Yes, this one, an. So we start from an plus 1, apply it here. At the end, we get what? 2 multiplied by an. Look here. We start from an, apply the solution. So we start from an plus 1, apply the solution. We get 2an, which is this one. So it's correct. When we solve an plus 1 using this solution, we get the right side. So we satisfy it for the recurrence relation. Now for the initial value. For the initial value means A naught. Apply A naught here. So A naught, A0, it's equal 2. Instead of n now we put 0, yes? So 2 power 0 multiplied by 3. So it's equal 1 multiplied by 3. It's equal 3. So correct. So we use this solution to get the initial condition correct. And we get this, we use this solution to get the recurrence relation correct. Then this solution is a correct solution for the recurrence relation. We will take many examples related to this issue. Okay, let me check the time. Okay, it's 10. Okay, in this example, same issue, solve the following recurrence relation. We have this recurrence relation, which is each term, it's equal previous term plus 3. Here, each term equal 2 multiplied by previous term. Here, no. Each term is equal previous term plus 3. So it's same like first sequence, this one. Okay, but when I ask you that we need term 100, it's difficult to find it here because we don't have the general form or general solution. By the way, when we find the solution like this, we can find easily any term. So if I ask you here, I need term 100, it's easy. You will set A100, it's equal to or 100 multiplied by 3. So you can calculate and get the term 100 without knowing the previous terms from this general solution. So let's get the general solution for this one with initial. Now it's different. We have initial A1, it's equal to. So the sequence actually here, it's 2. Okay, next term, which is previous term plus 3. So it's 5. Next term, it's previous term plus 3, which is 8. Next term, which is 11, and so on. So this is a sequence. So from this sequence, let's find the solution for this sequence. Okay, to solve this sequence or recurrence relation, recurrence relation, you have to find the terms. We already have A1. We will try to find A2. A2, it's A1 plus 3. A1, it's 2 from here. So it's 2 plus 3. A3, it's a previous one, a plus 3. A4, it's the previous one. It's come from here, a plus 3. Okay, let's try to make it as more easy to find relation. So here, 2 plus 3, okay. Here, 2 plus 3 plus 3 means 2 plus 2, 3 means 3 multiplied by 2. Here, this term plus 3. So it's 2 plus 2 multiplied by 3 plus 3. So 2, 3 plus 3 means 3, 3. 3 multiplied by 3 plus 2. So let's find AN. AN, look here. 2, it's constant. 2, 2, 2, it's constant. So we have 2, a plus. 3, it's constant. We have 3, 3, 3. So plus 3 multiply by. Multiply by what? Here multiply by 3, here multiply by 2. Here you can consider it that it's multiplied by 1 because 3 multiplied by 1, it's 3. Yes? So it's multiplied by 1, 2, 3. What's the relation between this and the term? Here term 2, it's multiplied by 1. Term 3, it's multiplied by 2. Term 4, it's multiplied by 3. So it's multiplied by the term minus 1. So this is the general solution. Term AN, it's equal to plus 3 multiplied by n minus 1. Now we need to confirm if this solution is correct. To confirm, we will start from the solution or from the recurrence relation. The idea, you have to start from one and reach the other one. So I will start from the recurrence relation this time. So AN, it's equal AN minus 1 plus 3. Now apply the solution for AN minus 1. So if we apply the solution for AN minus 1 here, okay, I will write it as AN minus 1. What its solution? It's 2 plus 3 multiplied by. Instead of n, we have n minus 1. So n minus 1, we still have another minus 1, minus 1. So instead of an here, an minus 1, we will write it as 2 plus 3, 2 plus 3 multiplied by n minus 1 minus 1. N minus 1, here's the term, which is n. Here, n minus 1 here. Minus 1. Okay, all plus 3, this constant, we take it as it. Now try to just reorganize. It's equal to plus 3 multiplied by n minus 1, it's n minus 2 plus 3. Just take the 3 from here and here as a common factor. So it's equal this constant 2 Okay, so constant 2, we take it here, a plus 3 and 3, we take it outside. What's still inside here? N minus 2 as it, a plus, we take this 3 outside. What is still inside? 1. Why 1? Because it's like this. When you have a 3 and you want to take it outside, you multiply by 3, divide by 3. Same idea. Take this 3 outside. What inside? Because when you multiply by 1, you did not change. What is still inside? 3 divided by 3 means 1. Yes? So here, when we take the 3 as a common factor outside, we still have 1. Okay, now reorganize this again. Okay, we reach here. So it's 2 plus 3 here. 2 minus n minus 2 plus 1 means multiply by n minus 1. Okay, look to this one. So when we have an, it's actually equal to plus 3 n minus 1, which is the solution. So we started from an here, and we reached the solution. So it's confirmed. It's a solution for the recurrence relation. Now, next step, we have to confirm that it's a solution for the initial value or initial condition. So we will apply it for A1. It's equal to plus 3 multiplied by n minus 1. N here is what is 1. So multiply by 1 minus 1. So it's equal 2 plus 3 multiplied by 0. This means 0 because 1 minus 1, 0, multiplied by 3 is 0. So plus 0 doesn't mean anything. So it's A1, it's equal to, depend on the solution. So it's correct also for initial value. So we confirm that it's a correct solution. Let's organize our ideas. So we have recurrence relation. To find the solution, first, we find a few first terms. Second, we find the general term. Third, we confirm it for the recurrence relation and for the initial condition. Now we have this general term. You can find any term. Now, if I ask you for this sequence or for this recurrence relation, what's the term? For example, 50, you don't need to calculate all the previous term. Directly, you will say, okay, term 50, A50, it's equal to plus 3 multiplied by n, which is 50 minus 1, so multiply by 49. Then you can calculate easily the value of term A50 without looking for previous terms. Of course, this have many applications in the real world. Anything that uh, have something repeated, like if you have animals and these animals get births usually, and you need to know after a few months or a few years how much animals you will get, like the interest compound in the bank. Okay, this bank give percent, okay, 10%, 15%. Okay, if I put 10,000 USD after 30 years, how much will be this the value of inside the account? Okay, and so on. It's have many applications in the real world. Anything that have something repeated in the real world, you can write recurrence relation, and from this recurrence relation find solution. Then from this solution you can find any term repeated, term repeated after 100, after 200, and so on. So actually it's applied for the way of recurrence relation. It's applied for the advanced counting, not the easy one like product and summation that we already gave you last time. Okay, this example only to we have the recurrence relation, we have the solution, and we need to check if the solution is the correct solution for the recurrence relation. So determine, check, or prove. This is the meaning of determine whether the sequence an, what's the sequence an, the solution for the recurrence relation here, for the general term. Check if this an, okay, for every non-negative integer, tell you that the terms, it's non-negative integer, means 1, 2, 3, and so on, is a solution. So we need to check if this one, it's a correct solution for this recurrence relation. So we have the solution, we have the recurrence relation. Recurrence relation means the recurrence relation with its initial values, so, or initial terms. We have two initial terms, and we have recurrence relation, and we have the solution. We need to check if this solution, it's a solution or a correct solution for this recurrence relation. The idea here, we check the if this sequence satisfies the recurrence relation and if this sequence satisfies the initial condition. For me, I see that usually it's better to start from the initial condition. We have to check both, but it's better to start check from the initial condition because it's much easy. If the solution not correct, usually it will not be correct for the initial condition. So if you find that it's not correct for the initial condition, no need for the next step to prove it for the recurrence relation directly from the initial condition. If it's not satisfies the initial conditions or the initial terms, then it's not correct. And you don't need the next step to check the recurrence relation. But if you start from the recurrence relation, it's take more steps, and at the end you find that the solution it's not correct, then you waste your time. So start usually from the initial condition. Okay. So for the initial condition, we have A0 and A1. So we will apply this one for the initial condition. Okay. This means we have to find from this one, we have to find A0 and we have to find A1 because we have two initial conditions. So A0, it's equal 3 multiplied by n. So 3 multiplied by 0, which is equal 0. A0 equals 0, depend on this solution. Look here, A0 equals 0. Okay, correct for the first initial term. For the second initial term, A1, okay, so n equal 1 here, so it's a 3 according to this. It's a 3 multiplied by 1, which is equal 3. It's correct because A1 here equal 3. So it's correct for the initial condition. Now let's check if it's correct. So this is a sequence. We need to check if this sequence here, or this solution, if it's correct for the recurrence relation. Okay. How to check it? We will start from this recurrence relation, apply the solution for each term. If you get at the end an, then it's correct. An means not this one. You start from this an or this one, and you reach this one. This means you reach an. Okay, let's apply it. So write the recurrence relation first, then apply the solution for first part and for the second part. So an here, an minus 1, it's equal according to here. It's equal what? It's equal 3 multiplied by n. It's become n minus 1 here. So multiply by n minus 1. Okay. The other part, it's an minus 2. An minus 2, same. We will apply it here. So when we have n minus 2, this means 3 multiplied by n minus 2. So it's 3 n minus 2. Okay, so this one, it's equal to multiplied by the solution, which is 3 n minus 1 minus, we take minus an minus 2, we find it here. So it's 3 n minus 2. Just simple calculation now. 2 multiplied by 3 multiplied by n. So it's 6n. 2 multiplied by 3 multiplied by minus 1. So 2 multiplied by 3, it's 6 multiplied by minus 1, it's minus 6. Okay, so continue. 3 multiplied by n minus 3 multiplied by n. So it's minus 3n. Minus 3 multiplied by minus 2, it's a plus 6. Minus 6 was plus 6. Gone. Okay. 6n minus 3n, it's equal 3n. Look to 3n here. What it's equal? It's equal an. So we start from the recurrence relation and we get that it's equal an using the solution. So the solution confirmed for, or this sequence confirmed as a solution for this recurrence relation, and confirms that it's a solution for the initial conditions. So this solution is a correct solution, or this sequence is a correct solution for the recurrence relation. Let's take another example. In this example, the solution actually, it's not a correct solution. So what will happen if it's not a correct solution? Look to the solution. Here's the solution. Here's a recurrence relation. And here's the initial values. Same idea. We will apply it for the initial condition or initial terms. Okay, if you said A naught here, so A naught equal 2 power n. So it's 2 power 0 because n is 0 here, which is equal 1. So it's correct for the first initial term. For the second initial term, A2 equal 2 power n, which is 2 power 1, which is equal 2. So it's correct for the second initial. Okay, so for the initial values, it's correct. Not enough. We have to check it for the recurrence relation. To check it for the recurrence relation, we start from this side of the recurrence relation and get an. If we get an, then it's correct. Okay, let's try to apply it. We start from the right side. We apply the solution for this term and for this term. So the solution for an minus 1, so an minus 1 means 2 power n minus 1. For this one, it's 2 power n minus 2. So this equal, let's continue here. So this equal 2 an minus 1, it's here. So it's 2 power n minus 1 minus as it an minus 2, it's here. It's 2 n minus 2 power n minus 2. Okay. We have to organize this and try to reach something like 2 power n. So if you take 2 power n, we need to get something like this, 2 power n. So let's solve this one first. 2 multiplied by 2 power n minus 1, it's actually 2 power n minus this side what? It's 2 power n minus 2. So to solve it, we will take, for example, we can take 2 power n outside. Okay. We can take 2 power n outside. So this one solution, there is many solution for it. We can take 2 power n outside. Then what inside? 1 minus as a common factor, yes? So 2 power minus 2. Look to this one. Is it equal 2 power n? No, it's impossible. So we started from an here as a recurrence relation, but we did not reach an of the solution. So it's not equal. This means it's not a solution. Here in my previous solution, I take an 2 power n minus 2 as a common factor. If we take it as a common factor, here you need what? If you take an minus 2, you need to add 2. So it's become 2 power 2. So it's 4. Here you have 1. When you make minus, so it's 3 multiplied by 2 n 2 power n minus 2. I think the solutions that I put here, which is 2n as a common factor, then you still have 1 minus 2 minus 2 power minus 2. It's much easier than this one, but same idea. At the end, it's not equal 2 power n, so it's not equal an. So we start from an, apply the solution, did not give us an. So the solution is not correct. In some cases, it's much easier to do some type of approve called disapprove using counter example. If we guess that, if we find second term, third term, fourth term, it's not correct, then it's much easy to use it. Why? Because if it's a solution, it should satisfy all the terms. Let's check it for term A2. Check this one, this solution for term A2. How to check it? We will find term A2, use the solution, term A2, use the recurrence relation. If they are not equal, then this solution, it's not a solution for the recurrence relation. So get A2 from here, A2 from here, it's equal 2 bar 2, which is equal 4. Okay, now get A2 from here. A2 from here, it's 2 multiplied by A1, because A2, then 2 minus 1, it's 1, A1, minus here 2 minus 2, which is 0, so minus A0 or A0. A1, where is it? It's 1. So A1, sorry, it's 2 here. So it's 2 multiplied by 2 minus A0, which is 1, so minus 1. So 2 multiplied by 2, it's 4. Minus 1, it's equal 3. And it's not equal 4, which is we get it from the solution. So the solution for term A2 give us 4, and the recurrence relation for A2 give us 3. So this recurrence relation, it's not this sequence, sorry, it's not a solution for the recurrence relation. Okay. As I told you, there's many applications that we can model it using the recurrence relation. So recurrence relation actually can model or can solve many types of solutions that have repeated counting. So it's for advanced counting problems that have something repeated in this counting. So you can make a recurrence relation and get solution. Then from this solution, you can find any term you want. So for example, find the compound interest. So compound interest is interest that give the percent that given from the bank each year. So if you need, for example, to calculate how much in the account will be after 20 years, after 10 years, after how to calculate it, you can make it using recurrence relation. We will get this example, or we will take this example. Counting rabbits on an island, it's actually a real life problem, okay, or a real case study for the recurrence relation. There's one island, I don't know its name, that have problem with the rabbits, okay. So the idea, if we have 10 rabbits today, after 10 years, how many rabbits we will have, knowing that, for example, this 10 rabbits will give you a specific number of new rabbits every, for example, few months or every year, then you make a recurrence relation and calculate. For example, determine number of moves in Hanoi puzzle. You know Hanoi puzzle when you have uh, like what we call it rings, okay, and these rings in three different places and have three different sizes, and you need at the end put them in one side from the bigger one to smaller one. Of course, we have many copies of this. Sometimes we have only three rings like this. Sometimes we have 5, 10, and so on. So how many moves you need, you can calculate using the recurrence relation. And so on, many problem, counting bit string with certain probability that it grows or repeated with a certain way. Let's take this example, then we can have a small break before continue the next uh, part. Okay, let me just check the time. Oh, it's difficult for us. Okay, modeling with recurrence relation. Let's take this examples, first example that we mentioned, the compound interest. Here, suppose that one person put in the bank 10,000 in a saving account with the bank yielding give, okay, 11% as interest compound annually. Annually means each year, per year, okay? How much will be in the account after 30 years? To find the term or the value after 30 years, first you need to make a recurrence relation because it's repeated. Every year you get this percent. So it's repeated. So you will find a recurrence relation for this repetition. Okay. Then from this recurrence relation, try to find the solution, means the sequence, then general term of the sequence. Then from general term, you can find the account value after 30 years. So we need to get AN, which is a general solution for the recurrence relation. First, you need to get the recurrence relation. Actually, the recurrence relation, it's very clear. Each year AN, it's actually, each year, it's equal the previous year plus, okay, plus previous year multiplied by 0.11. So AN means current year. It's equal the value in the account at the previous year. So AN equal AN minus 1. And we add the interest for it. How much the interest? 11%. We can write it as 0.011, 11%. 11% of what? Of the amount of the previous year. So 0.011 means 11% of the previous one, which is AN minus 1. Okay. So we can write this as 1.11, and we take AN minus 1 as a common factor. So AN minus 1. So in the account this year, AN, it's how much was last year multiplied by 1.11. So this is a sequence. But any sequence or any, recurrence relation, this is a recurrence relation. Any recurrence relation need initial condition. What's the initial condition? A naught first year before, not even first year, year zero, before you put any money in the account, you put first before you get any money, means as interest. You put 10,000. So A naught, it's equal 10,000. So now it's a complete recurrence relation. We have AN equal 1.11 multiplied by AN minus 1, means this year it's 1.111 multiplied by previous year. And the initial condition is A naught equal 10,000. Now from this one, we have to find the solution. How to find the solution? It's easy. We said to solve this recurrence relation, so first step, we find the recurrence relation. Second step, we find the general term or the sequence as a solution for it. To find the sequence as a solution for it, get first a few terms. From this first few terms, you will find the relation. Okay, get first a few terms, then we will get terms A1, A2, A3, and find if there is a sequence. So each term, for example, term A1, it's 1.11 multiplied by previous year. For year A1, we have A naught or A0 as a previous year. A naught, we already know it. It's 10,000. Yes. So it's 1.11 multiplied by 10,000. This A1. A2, it's A1 multiplied by 1.11. So 1.11 multiplied by A1. What A1? Here. It's A1.11 multiplied by 10,000. So it's become 1.11 to power 2, because this multiplied by this one, 1.11 multiplied by 1.11 means 1.11 to power 2 multiplied by 10,000. Same issue A3, every time you multiply with 1.11, so you will increase here, it's become power 3. As you can see, there's a relation here. It's power 3 when we have A3. It's power 2 when we have A2. It's power 1 when we have A1. Yes? So the general term is AN equal 1.11 power n multiplied by 10,000. This is the solution or the sequence that satisfies this recurrence relation. Now, next step. Okay, so first step, we find the recurrence relation. Second step, we find the solution. Third step, it's to verify or check if this solution is a correct. We have many ways. We already give you here some ways. Okay, disapproved way. Okay, start from the recurrence relation and reach here, for example, start from the recurrence relation. Okay, and get the solution using the solution. So we have also one way that we already took it before, which is proved by mathematical inductive. Mathematical induction, we first verify it for the basic step, means for the initial value. Then we have to check the inductive step. What's the inductive step? We assume that it's correct for AK, then we check it for AK plus 1. So for the basic step A naught, apply A naught here. So A naught, it's equal 1.11 power 0 multiplied by 10,000, 10,000. So this one, it's equal 1. Anything power 0, it's equal 1. 1 multiplied by 10,000, it's 10,000. So when we apply the solution for A naught, we get 10,000. So it's correct for the initial condition or for the basic step. Now let's check it for inductive step. Inductive step means the recurrence relation here. For the inductive step, we assume that it's correct for AK. So we assume that the solution is correct for AK. Okay, where? Here. We have the solution, yes. Here's the solution. We will consider that this solution is correct for AK. So for AK, it's equal 1.11 power K multiplied by 10,000. Okay. We consider that it's correct for AK. So this is inductive, we already mentioned it. Okay, now we need to check it for AK plus 1. So we use the mathematical induction to prove that the solution, this solution that we find it's correct solution. Let's apply it for AK plus 1. For AK plus 1, it's equal 1.11 power K plus 1. Yes, multiply by 10,000. And this equal 1.11 multiply by 1.11 power K. Yes, because power K plus 1 means we can take 1.11 multiply by 1.11 power K, all multiply by 10,000. Look to this part. It's same as AK, yes? So it's equal 1.11 multiplied by AK. So so what's this one? This one is the solution, which is AK multiplied by 1.11. We applied this here. We applied it here for this one. So AN equal 1.1. And it's equal at the end, this part multiplied by a K, which is give us, seems I start from down to up. Let me just, I don't want to confuse you, but I should start from up to down, not the opposite. So for AK plus 1, it's only a way. You can use the previous way to prove it. But if we use AK plus 1, and we need to apply it here first for the recurrence relation, because always we start from recurrence relation and get the solution. This idea, we need to get, if it's correct, we will start from the recurrence relation and get the solution. If we start from recurrence relation, AK plus 1, this K plus 1, this K plus 1 minus 1, so it's K. So it's 1.1 multiplied by AK. This is from the recurrence relation. Now, by inductive hypothesis, we know that from hypothesis, we said that this is correct. So we will put it instead of AK. So we still have 1.11, and instead of K, what its value here? It's 1.11 power K multiplied by 1.11. This from the inductive hypothesis. So just reorganize this power 1, this power K, it's power K plus 1 multiplied by 10,000. Look, this one, it's the solution for A K plus 1, which is 1.11 power K plus 1 multiplied by 10,000. So what this mean? This mean we start from the recurrence relation, apply it here, and we use our hypothesis here, the inductive hypothesis, and at the end we get the solution, sum of the solution. So we start from the recurrence relation, get the solution. This means it's correct for AK plus 1. So it's correct for AK and it's correct for the first one. So this solution is correct. If this solution is correct, we can apply it. So we can apply this solution and find any year. What we need to find year A30, because we said how much will be after 30 years. So A30, it's equal, instead of n, now we use 30, it's 1.11 power 30 multiplied by 10,000, and this number can be calculated. When you calculate it, you will find this number. It doesn't matter to calculate this final value. Okay, now we have another subject. What's the time now? Sorry, we cannot have break actually because it's long subject. So we will try to finish on time instead of take a break, okay? So, solving linear recurrence relation. Now we will speak about one type of the recurrence relation, and there's two theorems to solve this type of recurrence relation. Okay, so here we will speak about only linear recurrence relation. Okay, what's this mean? What's this mean of linear recurrence relation? Recurrence relation, it's equation to repeat some calculation, yes? You know the linear equations. Let's take the terms. Okay. This only just as a review because it was in a different lecture last years, but now it's in the same lecture to just review for the term, which is the initial conditions, the recurrence relation, and the sequence. It's a solution for the recurrence relation. Just review. Now let's speak. What's the meaning of linear recurrence relations? Okay, we have two types actually of linear recurrence relation. We have homogeneous linear recurrence relation and non-homogeneous linear recurrence relation. our focus only in the first type, which is linear homogeneous recurrence relation. So we will take this type, linear homogeneous recurrence relation. Okay, we will not take this type, linear non-homogeneous, because it's have another way of solution which is out of our scope. We will not focus on it. So what's the meaning of linear homogeneous recurrence relation? With, and this is important also, with constant coefficient. We will not take recurrence relation with non-constant coefficient, only with constant coefficient. Okay, what's the meaning of constant coefficient? What's the meaning of linear? What's the meaning of homogeneous? What's the meaning of degree of the recurrence relation? Like any equation, it have a degree. So actually, if we have this recurrence relation, an equal C1, C1 means any number, any real number, multiplied by term an minus 1, C2 multiplied by term n minus 2, and so on until Ck means the constant Ck an minus k. This general form for linear homogeneous recurrence relation. Okay, what's the meaning of linear? As you can see, all the terms have a. So we have only one variable here, which is a. We don't have more than one variable. So if all the variable or all the terms have same variable, we called it homogeneous. So this is the meaning of homogeneous. No term other than the multiplication of A may be in another relation, multiplication only of multiplies of B or F, means we have only one variable here. One variables inside all the terms, so it's homogeneous. What's the meaning of linear? Okay, you know here, when you speak about numbers, okay, some equations give you lines. Some equation give you curves. Some other equation give you like pulse, like this. Linear equation will give you only lines, or linear recurrence relation. Its equation will give you only lines. That's why we called it linear. When the equation give you line, only if its exponent is 1. If you have a square, for example, a power 2 or a power 4 or a power 3, it's not linear. To become linear, you have only a, means a power 1. Okay, because a means a power 1 or f power 1. If you have any other exponent rather than 1, this means it's not linear. So this is the meaning of linear, this is the meaning of homogeneous. What's the degree? Degree actually, it's how many terms we have. You will know it from n minus which number? N minus 5, for example, n minus 2, or so on. So from this one, you will have the degree. What's the meaning of constant coefficient? Constant coefficient means all this constant, it's numbers, not variables. This is the meaning of constant. So coefficient in front of terms are constant number, not general function or general variable. Okay, from this term, let's see those relations, recurrence relation, and identify which one is linear, homogeneous recurrence relation with constant coefficient. So let's take linear L, homogeneous H, recurrence relation with constant coefficient C point C, for example, or C. So linear, which one of this linear, which one not linear? Let's check. This one is linear. We have any power here? No. So it's linear. This one, it's not linear. Why? Because we have power 2. So this one not linear. This one linear because we don't have any power. This one linear because we don't have any power. This one also linear. We don't have any power. This one also linear. Okay, now let's speak about homogeneous. Which one homogeneous, which one not? We have only variable p here, so it's homogeneous. Here we have variable a only, so it's homogeneous. Here we have variable f, so it's homogeneous. We have variable h, it's homogeneous. No, it's not correct. All the terms must have this variable. Here, this term have constant only. When you said this term have 1 only, or 3 or 5, this means it's multiplied by variable to power 0. So maybe this multiplied by x power 0. So if it's multiplied by x power 0, it's equal 1. Maybe it's multiplied by h power 0. We don't know. So this one, it's not homogeneous because this term, it's constant without the variable. So it could take any variable. So this one, not homogeneous. This one, homogeneous. This one, homogeneous. This is the coefficient. Here, it's the variables of the, okay, of the equation. Now let's see if constant coefficient or not. Okay, first one, 1.11, it's constant coefficient. Here, 1, here, 1, so it's constant coefficient. Here, 1 multiplied by f, here 1, from where? There is no 1. Actually, this means we have constant 1 because 1 multiplied by f, it's f, yes? So it's constant coefficient. Here, we don't care because actually it's constant coefficient, but it's not homogeneous. Here it's constant because 1 multiplied by a. Here it's not constant. We have n here, and n it's variable, not constant. So which one of them it's linear, homogeneous recurrence relation? As you can see, this one, it's linear, homogeneous recurrence relation. This one not. Why? Because it's not linear. We have power here, power 2. This one, it's linear, homogeneous recurrence relation with constant coefficient. This one, it's not homogeneous. This one, it's linear, homogeneous with constant coefficient. This one, it's with not constant coefficient. So our focus will be on this type, linear, homogeneous with constant coefficient. So this one, it's in our scope. This one, it's in our scope. This one, other, it's not in our scope of this lecture. Okay. Let's speak how to solve this linear homogeneous recurrence. Okay, if we find a recurrence relation and it's linear and homogeneous, how to solve it? To find a solution, and from this solution we can find any term, yes? So, first proposition says like this. Proposition means some statements to help you for the solution. It says like this. If we have this recurrence relation and its linear homogeneous recurrence relation, if we find two solutions, an, its first solution, a comma n, or any name, it's the second solution. So as I told you, for one recurrence relation, we could have more than one solution. Here, if we have two solutions, then the solution of the recurrence relation, it's the summation of the first solution, first sequence, plus second sequence. So we will try to find two solutions or more, could be more. The summation of all solutions, it's actually the solution for the linear homogeneous recurrence relation. Okay, but we said we have in the solution constants. How to find this constants, I will show you later. We said that it's not enough to have recurrence relation. We have to find the initial conditions also, or the initial value. If we said that the initial value dn, then it's equal alpha multiplied by an. Okay, if we have two solutions, then first initial condition alpha multiplied by an, second one it's alpha multiplied by a comma n, and so on. Then later this constant alpha, it's the constant. We need to find it. Okay, what's the meaning of all this? Okay, don't confuse. Let's take examples. Okay, by examples it will be clear inshallah. But before find example, how to find two or three or more solution. Actually, recurrence relation, if it's linear homogeneous, we can try to convert it into something called a characteristic equation, because we know how to solve the equations like okay, x plus 1 all power 2 equals 0. It's equation. We know how to solve it. We know how to solve x power 3 plus something equal 0 if we have only x, because it's homogeneous, yes? So recurrence relation, it's difficult to solve it. So we will transform it to something called characteristic equation. And from it, we will try to find a solution. So if we find solution R, for example, then if we find maybe R1, R2 as a solution for the recurrence, for the characteristic equation, then each solution an, a comma n, and so on, it's R, which is a solution for the characteristic equation power n. What's the characteristic equation? What's R? What? Let's take them like this. We have here a we have here a recurrence relation. How to get characteristic equation from it? To find characteristic equation, we need to write it as r power n. Instead of an, I will write it as r power n, r power n minus 1, r power n. So rewrite this with r. Instead of an, a, base n, we will write it as r power n. This is a characteristic equation. Okay, because equation with power 1, power 2, and so on, it's easy to solve it using the normal way of solving equations. Okay, so I will rewrite this one as this. an, it's rn, equal c1, c1. an minus 1, it's rn minus 1. And so on until ck and an minus k, it become rn minus k. Now, all this side, move it to the other side. If you move from left side to right side, or from right side to left side, a plus become minus, minus become plus. Yes, so we have rn minus this one, minus c1 rn minus 1, minus c2 rn, until minus ck r. What is still here, if we move everything to the left side, we have 0. Okay, now to make it much easier, divide everything. If you divide left side and right side by the same thing, you will have same result. So I will divide left side by r to power n minus k, and divide this one by r power n minus k. 0 divide anything, it's 0. This one, okay, rn minus k, take this one, so we have c power k. We will define everything as, sorry, ck. Minus, minus, minus. This one, if you divide it, okay, it's become like this. Instead of n goes with n, then you have k minus 2, yes? So k minus 2, k minus 1, and instead of n, now we have k. What is k? K, it's the degree. So it's easy to find it as number, but if you keep it as n, it's another issue. It's difficult to find n. Okay, that's why we divide by r power n minus k. So it's easy way to find the characteristic equation. By example, I will show you. So from this one, we will find this one. So an, it's become r power k, r power k minus 1, until you reach constant without r, yes, equal 0. Then you can solve this equation. Okay, let's take it by example. Find characteristic equation for this one. Who knows this one? It's Fibonacci series, yes. Fibonacci characteristic equation. It's linear, yes. It's homogeneous, yes. It's with constant coefficient, yes. Convert it to characteristic equation. Fn, it's become r power k. Okay, what k? Look to the last minus value, n minus 2. This means a degree, which is k equal to. So rk means, r power k means, because k it's 2, so r power 2. Minus, this one become there, it's become minus. R k minus 1. Instead of n, we will write k. K minus 1, it's what? K, it's 2, it's become 1. So r power 1. After you use many times, you will see that you can apply it without all this calculation. This one comes there, so it's minus r power what? K, which is 2 minus 2. So 2 minus 2, it's 0. R power 0, it's 1. So it's minus 1. So this is a characteristic equation. So shortly, r power k, here, if you could have constants, the minus of the constant, r power k minus 1, until last one will be what? The minus of the constant alone, without any r. Because at the end, n, it's same like k minus this number. Okay, so here I will make it directly. Look to the last one. This is the k. So we have r power k, which is power 3. This minus go there as plus r power 2. This plus go there as minus. So minus 4 r power 1, r power 3, r power 2, r power 1. This plus become there minus 4. R power 3, R power 2, R power 1 without R. This is the characteristic equation, but you have to focus. Maybe this term is not exist. If this term not exist, then this one not exist in the characteristic equation. So you have to sure that all the terms exist. Okay. Second proposition. Now we speak about how to get the characteristic equation. In this proposition, we will speak about how to find the solution. To find the solution of the characteristic equation, we have to find R as a solution or set of solutions for the characteristic equation. So if we have this characteristic equation, and this characteristic equation, it's a characteristic equation for this linear recurrence relation. This means if R is a solution, how to get R as a solution? As you can see here, what's this? It's actually equation, a quadratical equation. It's easy to solve it, and from the solution we could find one solution R, we could find two solution R1, R2, like an equation. We will take some examples to solve the equation, but you yourself, you have to know how to solve this easy equation. Okay. So if you find R as a solution for the characteristic equation, R power n, it will be a solution for what? For the linear homogeneous recurrence relation. Okay, what if I have R1, R2, then R1 power n plus R2 power n is the solution for the recurrence relation or linear homogeneous recurrence relation. But we need constant for each solution. Okay, later we will speak about this because we have theory that give you how to write the solution. When you find solution for the recurrence relation, write it as a solution for the linear homogeneous recurrence relation. Okay, so let's see this one. Consider the characteristic equation for this one. Actually, this characteristic equation, we just saw it here. It's characteristic equation for this recurrence relation. How do we know? Okay, r power 2, which is fn. So we have fn or an or xn, okay, equal. This minus become plus, yes, for f, this fn. This means this fn minus 1. Okay, plus, when it's go there, it's become minus. Minus what? Minus 4. Multiply by what? F, this n minus 1, this n minus 2. And so on. So it's easy to find the recurrence relation from the characteristic equation and the characteristic equation from the recurrence relation. Okay. Now let's focus only on this one. We have this recurrence relation. How to solve it? It's actually a difference between perfect square. You know the perfect square, r minus 2. It's different between perfect square, power 2. What its solution? Power for first term, it's 2 power r power 2. Then minus 2r multiply by 2, so minus 4r. Both sides multiply together, multiply by 2. Then the power or the square of the second term, which is a plus 4. So this equation, it's very famous equation. So if we have this characteristic equation, we can write it as a perfect square, which is equal here 0. This means take the root for both sides, so we don't have power here. So this means r minus 2, it's equal 0, because root of 0 is 0. Root of this one removes the power. And from this one, we find that r equal 2. We said if this characteristic equation it's for this recurrence relation, then the solution r for this characteristic equation, it's r power n for this recurrence relation. So we find r as 2. So if we find r as 2, then 2 power n, it's one solution for the recurrence relation fn blah blah blah. Okay, we can confirm it. Yes, check it. Check it to confirm it. I don't want to check it again. Let's move to next one, which is theorem 1. Theorem 1 says like this. Theorem 1, actually, it's applied when we have two solutions. Okay, so when in the characteristic equation, when we have R1, R2, we apply this one. Also, if we have R3, we can apply this one. Okay, so at this theorem, we said if we have this characteristic equation, and this characteristic equation, it's come from this recurrence relation, then if we find R1, R2 until Rm, it's all a solution for the equation, means for the characteristic equation. Okay. And we have some constants that we don't know, alpha 1, alpha 2, until alpha m. If we have m solution, we have m alpha, m constant. Then an, which is the solution for the recurrence relation, it's actually equal. First constant multiplied by first solution r1 power n, a plus. Second solution, second constant multiplied by R2, which is second solution power n, and so on. Okay, so if we have two solutions for the recurrence relation, then an equal alpha 1 first solution power n plus alpha 2 second solution power n. Okay, what alpha 1, alpha 2? It's easy to calculate alpha 1, alpha 2 if we have for the recurrence relation initial value. We will use the initial value to get the constant. Okay, if we have three solutions, it's easy. If you have three solutions for this characteristic equation, then the solution, for example, R1, R2, R3, then the solution for the recurrence relation, an, it's equal alpha 1 R1 power n plus alpha 2 R2 power n plus alpha 3 R3 power n. So if we have two solutions until here, if we have three solutions until here, if we have four solutions, we complete, and so on. Okay, so now first example, let me see, just check the time. Okay, we still have time, hopefully to finish, inshallah. Because if we did not finish the whole lecture note, we will have extra lecture this night. If we did not finish, I will give another 1 hour, maybe starting from 10:30 tonight until 11:30. From 10:30, we finish 11:30. Okay, if we did not finish, hopefully we will finish. Anyway, I will give for the other section, the section A we did not finish, group A we did not finish. So I will give them tonight, inshallah, one extra lecture. Hopefully, I will not need for you also. Okay, so let's see this example. Okay, so in the example is give you recurrence or linear homogeneous recurrence relation with some initial value. And the question here, what is the solution? Or solve this recurrence relation. To solve this recurrence relation, use theorem 1. Okay. First step is to find the characteristic equation. So first step, find the characteristic equation. How to find it? Okay, an, it's Rn. Here we have plus 1, plus it's become minus there. So minus, from where you know that it's bar 2. I forget to tell you in this example, but I told you before. First of all, you need to know the degree here. It's last one, it's minus 2. So the degree k, it's equal 2. Yes? So first R will be R power 2. Then on n minus 1, it will be R power 1, which is 2 minus 1. And why it's minus r? Because we have to send it there. Then 2 minus 2, it's 0, so we don't have r. We have only 2. Send there, it's become minus 2. So this is the characteristic equation. R power 2 minus r minus 2 equals 0. This equation, it's a quadratic equation. Quadratic equation, you know how to solve it. Yes? You know or not? If you click to this link, I already give you here. After this slide, just a help for you for solving the equations. It's like a revision for how to solve equations. Okay? How to solve equations? We have many types of equation. For example, perfect square equation. When you have something like this one perfect square, this one different between perfect square. How to solve it? Here, example. You can review the example at your house, or you can see it. Actually, this A plus B, because as you can see here, A square, B square, A multiplied by B multiplied by 2. This means we have A plus B multiplied by A plus B, which is A plus B squared. Okay? And this different between perfect square. From where I get, okay, it's power of A, power of B, then B multiplied by A multiplied by 2, but minus. So it's actually A minus B power 2. Okay, also we have different of squares. How to solve it? Different of square if we have A2 minus B2. This means it's actually equal A plus B multiplied by A minus B. Then how to solve it? A plus B equals 0. This means A equal minus B. And this one, A equal B. So we have two solutions. A1, which is equal minus B. A2, which is equal B from this one. B could be any number, maybe 10, 5, or something like this. So this is a perfect square. This for general rule for quadratic equation. General rule says if you have quadratic equation like this, then the solution will be like this. X equal minus this constant, which is B, plus minus the root of B power 2 minus 4. AC, A, the constant with X, X square. C is the constant alone without the variable. Okay, all divided by 2A. Look here, we have a plus minus. This means we will have two different solutions. When it's a plus, when it's minus. So the two different solutions. So we have two different solutions for quadratic equation if it's not perfect square. If it's perfect square, we have only one solution. If it's not perfect square, if it's different of squares or any other quadratic equation, you will have two solutions. I give you also solve of polynomial when you have x power 3, even if it's have x power 4 or something, it's same way. I will give you this examples when we have these questions. Okay, seems we will reach same place as previous section. What's the time now? Oh, it's almost 10 minutes. Let me just give first example, then we will take extra lecture tonight for both group. For you, group A and group B, we will not use the same team code. I will share a link with you because I have together both of you, the two groups in the same section, okay? So I will give extra lecture tonight, 10:30. It will be around 1 hour, inshallah. 10:30 p.m. tonight. Because this subject is important and it's in the midterm exam. Okay. So if we need to solve this one, we need to use, let me copy it, okay? 2 power r power 2 minus r minus 2 equals 0. This equation, I need to solve it. Solve it using this general rule. Okay, this general rule. So this our equation. We need to solve it. To solve it, I need to identify what is A, B, and C. What is A here? A equal 1. What is B? B equal minus 1. Here, C. C equal minus 2. Okay, now let's apply this rule. So R, instead of X now we have R. R equal minus B. Is it B or A? I think it's B. Yes. So minus B, which is minus minus 1, it's become 1. A plus minus root of B power 2, which is 1. Minus 1 power 2, it's 1. Minus 4 multiplied by A, which is multiplied by 1, multiplied by C, which is minus 2. All this divided by 2A. A, it's 1, so it's divided by 2. So R equal 1 plus minus root 1 minus. Okay. Minus what? Minus 4 minus 4 multiplied by 1 multiplied by 2. So it's become plus minus minus. It's become a plus 8. I think, is it our equation? Is it minus 2 at the end? Yes. So y minus r minus 2. I want to sure, but if it's same, yes, minus 4 minus 2. So A multiplied by B, so 4 multiplied by A, which is 1, multiplied by, so it's plus 8. So it's correct. I thought I get another equation mistakenly. No, it's our equation. Okay, all divided by 2. So it's equal 1 plus minus root of 9 divided by 2, and it's equal 1 plus minus root of 9, it's 3, because 3, it's 3 power 2, it's 9. So root of 9, it's a 3 divided by 2. So we have two solutions, R1, R2. R1 when we have plus, R2 when we have minus. So we have 1 plus 3 divided by 2, which is equal to this R1. R2, we have 1 minus 3. We take 1 times a plus, 1 times a minus. Minus 3 divided by 2, which is equal minus 1. So R1, it's equal to R2, it's equal minus 1. This is the two solutions using this rule. Okay, so this is the two solutions. We have these two solutions. R1, it's equal to R2, it's equal minus 1. Depending on the theorem, this theorem, it says like this. The solution AN will be alpha 1 multiplied by first solution power n, alpha 2 multiplied by second solution power n. So AN, which is the solution, it's alpha 1 multiplied by first solution, which is 2 power n, a plus alpha 2 multiplied by second solution, which is minus 1 power 2. This is the solution. But we did not finish. We have to know what is the value of alpha 1, alpha 2. We have to find the constant. To find the constants, we have to use the initial conditions, the initial values, this one. We will find A0, A1 using this solution, then we can find alpha 1, alpha 2. And you have to know that here, number of result here, or number of solutions for the characteristic equation must be at least same number as the initial condition to get this constant. Because to get two constants, we need two initial values. Okay, now to get it, let's take A naught, A0. So if we said A0, it's equal alpha 1 multiplied by 2 power 0. Because now we said n, it's equal 0. Yes? What's the meaning of A0? This means we write this one with n equals 0. Write it with n equals 0. So A0, it's equal alpha 1, 2 power 0 plus alpha 2 minus 1 power 0. A naught, it's equal to, so this one, it's equal to. So 2 power 0, it's 1. 1 multiplied by alpha 1, it's alpha 1, a plus alpha 2 minus 1 power 0. It doesn't matter what's the number. If it's power 0, it's 1. Anything. Wall power 0, it's 1. The table power 0 is 1. The chair power 0 is 1. Any number in the world power 0, it's 1. 1 multiplied by alpha 2, it's alpha 2. All this equal to. So we have alpha 1 plus alpha 2, it's equal to. From A1, apply A1 here. So A1, it's equal alpha 1, 2 power 1, so multiply by 2. A plus alpha 2 minus 1 power 2 because power 1, so it's minus 1. All this equals 7 because A1 equals 7. Okay, so we have one equation, another equation. So the other equation, we have alpha 1, 2 alpha 1, 2 here, a plus alpha 2 multiplied by minus 1, it's equal 7. We can solve it and get alpha 1, alpha 2. How to solve it? From first one, you can write it like this. You can write it alpha 1 equal 2 minus, we send this other side. It's plus become minus, minus alpha 2. Okay. So let me just clear the screen here from this one. Okay, so this alpha 1, instead of alpha 1 here, put alpha 2. So let me write it again. So it's 2, 2. Instead of alpha 1, now it's equal what? It's equal 2 minus alpha 2. So multiply by 2 minus alpha 2 plus what? Not the plus, let's minus now. Minus 1 alpha 2. All this equals 7. Now we have only one unknown value, which is alpha 2. So we can find it. So this one, 2 multiplied by 2, it's 4 minus 2 alpha 2, all minus 1 alpha 2 equal 7. From this, we can find that minus 3 alpha 2 minus 2 plus minus 1, it becomes minus 3 alpha 2 equal 7. This send it to the other side. So 7 minus 4, it's equal 3. So 3 with minus 3, then alpha 2, it's equal minus 1. Okay, now we have alpha 2 equal minus 1. We can get alpha 1 from here. Alpha 1 equal 2 minus alpha 2 minus alpha 2. Alpha 2 is minus 1 minus minus 1, so it's become plus 1, which is equal 3. So we find that alpha 1 is 3, alpha 2 is minus 1. So to find the final solution now, we have to put alpha 1 and alpha 2 in their position. So this one become A2 equal alpha 1, which is 3, multiplied by 2 power n minus 1, because alpha 2 is minus 1. So minus, okay, minus 1 power n, minus 1 power n. So this is the solution for this linear homogeneous linear homogeneous current recurrence relation with constant coefficient. We have more examples to solve, but we don't have time, and we have another theorem here that we have to take it. It's important also. So let's take extra lecture, inshallah, tonight. I will give you more examples, and I will give you the second theorem, inshallah, tonight. So we will have one extra lecture. I can send you a previous exam to practice. However, maybe this exam will be different. I will tell you if the exam is different way. because we did not until now decide the way. I'm still discuss with Dr. Borhan, and I will give you the information. Anyway, you have to study at the same way. It's not necessary to know how the question exactly, yes. But when we decide, I will tell you how it will be exactly. But you have to study for the exam. Anyway, we have, inshallah, one extra lecture tonight, 10:30. I know it's late, 10:30, but the prayer, it's finished almost 10. So we will make it 10:30. I hope it will be short, inshallah. It's important to attend it, but the attendance, I will not take the attendance. I will send you link for uh, the extra lecture tonight, because you as a group B and the group A will be at the same lecture. Okay, so we cannot use uh, same team group. I will create a new team group only for this extra lecture. Okay, and I will share the link with you. Okay, see you tonight, inshallah. Assalamu alaikum.